Hello everyone. In this video we are going to use Excel to help us answer questions when we are talking about the central limit theorem. So from this one we're going to use the same scenario as before. So remember Harry from last time, he was working with Jack. Another trainer came up to him to reveal the secrets of the central limit theorem. Harry was so impressed he decided to want to crunch some numbers. During these games, they have a row off to see how far athletes can row in 4 minutes. At this competition, they have an event called Battle of the North Seas, where the athletes are randomly assigned to teams to compete in Viking-inspired rowing events. Overall, we know that the average 4-minute rowing distance is about 800 meters, with a variance of 211,600 meters squared. They know that the distances are not normally distributed, so report the answers accurate to 3 decimal places. Okay, so here we have a scenario where we know that the original distribution is not normally distributed, but because we have a sample size that is large enough, we can actually justify that the sampling distribution, or the distribution of the means, is in fact normally distributed. So let's look at this. The mean that they have for this event is 800 meters. So we'll put that in with our mean. Our standard deviation is going to be equal to the square root of 211,600. Okay? And we've got a sample size of 83 because we're putting 83 peoples into these groups. So we've got 83 here. And our standard error, which is the standard deviation of the sampling distribution, is in fact like 50.49. It is the standard deviation of the original distribution divided by the square root of the sample size. Okay, so for the first group, we did teams of 83 called random speed, and it says what percent of teams can average above 838 meters. Okay, so this is a values question. It has given us a value here, and we want to know from 838 and above. So we've got 800, we've got 838 is somewhere in here, and so I'm going to say about like 40 or 45% can average above 838. So let's see if that's right. So we've got 838, and then to the right we want, I don't know, we'll put in like 1,000. It just needs to be a really big number off to the right. And if we hit enter, it says, okay, so I was wrong with 40, but it got me in the ballpark of like 22%. And we see that when we check our answer over here, give me just a second. There we go, 0.22, oops, okay. There we go, 0.2258, 0.2258 is what we got. Okay, next question. How many standard deviations away from the mean is the target distance for ramming speed? So we've got this target distance up here of 838, and we want to know how many standard deviations away it is. That is a question of asking for our z-score. Remember, our z-score is going to be our x bar minus mu divided by our standard error. Okay, so it's very similar to the one that we use when we are talking about a single observation. But instead of using just an x, we are using x bar. So that's the mean. That's the sample mean. And the standard error, we are not using just the standard deviation, but the standard deviation divided by the square root of the sample. Okay, so let's actually calculate this value out. So it's going to be equal to our x bar, which is 838. That's the average that we're wanting to know if the teams can average this much. 838 minus our mean and divided by the standard error. We've already calculated it, so I'm just going to click on it. And we have 0.75 standard deviations above the mean is our z-score. Okay, for the second event, they group into teams of 35 called rating party. What percent of teams can average above 838? Okay, well, everything here is the same except for our sample size. So here we're just going to update our sample size to 35. And we can now check to see, okay, what percentage in groups of 35 can average above 838? Now we've got 31% of groups. And then how many standard deviations away from the mean is this target distance? If you notice, because all we did was just click on references, it updated this as well to 0.4887. There we go, 0.4887. These two questions are identical, except these two are using a sample size of 35, and these two are using a sample size of 80. Okay, so coming on down. Jack, remember, he was the promising athlete from last time, wants to know what his team should average if they want to get into the top 5% of ramming speed and rating party. Okay, so the first one was ramming speed. So we want that to be 83. And we want to be in the top 5%. So we've been given a percentage. And the top 5% is going to be like over here. So the top 5% is also the same thing as like the, is also saying like from the bottom 95. So from the left, I want to go to 0.95. And to the right, I want to go to 1 to 100%. And so the range for this is from 0.8 is 883 meters all the way up to infinity. That's the top 5%, what they do. So we need to get at least this this 883 meters, 0.051. So let's take a look at that. Yep. Now, if we're talking about a smaller group, let's just change our sample size and let's see what happens to our distribution. Remember, the central limit theorem says that as we get a bigger sample size, the distribution is going to become narrower and more normal. Okay, but let's look at this if we were to run a sample size of only 35. We use a sample size of only 35. Look how much wider we are. So the edges are like at 600 and like 1100 over here. We go back into our 83. Notice how it's more like 700 and 900. So it's way narrower when we have a larger sample size. Let's go back to 35. Okay, so for 35, now the top 5%, which is what we have here, this left cut of the range is like 927 meters and a little bit extra. Rating party, there we go. Okay, why is the distance from the mean for the top 5 less for ramming speed than for rating party, considering the following graphics? Okay, so we went through and looked at these two graphics, but here they are again. So the rating party is like wider, and the ramming speed is narrower. So here we go. Let's look at our correct answer. So here, it's more rowers in ramming speed means that the standard error is smaller, which makes the distance to the top 5% to the mean closer than that of rating party. So essentially it's saying that, hey, our standard error, or the distance to our inflection point, is narrower for rowing speed than it is to the inflection point for rating party. And as that standard deviation gets smaller, it means that the distance from the mean to the top 5% is narrowed down. And so that's why our distance for rowing speed is smaller. Okay, well, that's how we can go through some of our central limit theorem questions utilizing our tools and some of our calculations here in using Excel. Remember that if we are going to actually calculate these values out, like if we want to run these values here, the equation that we want to be using is this norm.dist, and it allows us to choose our critical points, our means, our standard deviations. If we're in the central limit theorem, that standard deviation is going to be the standard error, and the cumulative distribution, we want that to be true. Now, the quantiles, there's actually a cool equation there for it as well. We can do equals norm.inverse and do a parenthesis. And now it says, okay, instead of giving us a critical point, now it wants a probability. Norm.inverse always measures things from the left and takes you to whatever percentage you want. So if we did norm.inverse here, let's do the bottom 15%, comma, the mean, comma, standard deviation, comma, true. That cutoff point for, oopsies. Oh, sorry. We don't need true. We do need deviation. it's going to give me to like 700, which is right about here for the bottom 15%. Now, if I want to do the top 15%, I would have to do 1 minus this guy, and it'll give me 880, and it flips it over to where the top 50. Anyhow, that's how these quantiles are working. If you want to do some digging into how these calculations are made, you can like double click on these, but I actually have some more calculations going on. So let me just type these out one more time. So it would be equals norm dot dist if we're going the value direction. So that is kind of what's happening here. And for the quantiles, it's norm dot inverse, and using those calculations. Anyhow, that's how you use this in order to calculate some basic central limit theorem questions. Best of luck to you on your own problems.